Welcome to my talk. As Professor Kalle said, I'm a PhD at Professor Mathes's chair, SEBIS, Software Engineering for Business Information Systems. And today I want to talk about a first study of maximal extractable value, or MEV for short, that we do on the Algorand blockchain. And I'm kind of a bit lucky because Barnaby already introduced MEV to you. Otherwise, the talk would last at 40 minutes or something. So the idea of this study is that this is a work in progress, so I'm not going to share like all results with you, but more of like a research plan. And the motivation is that, as you have seen, MEV is already studied in Ethereum extensively, and we are also doing that. But it's not an incentive inherent to Ethereum only. There are other blockchains as well with similar properties, and the properties or the dynamics of the blockchain kind of shapes how the MEV game is played. So it's like you can think as the blockchain as a cup and MEV as the water, and it basically takes the shape of that cup you put in. So because Algorand is a blockchain which has distinct properties compared to Ethereum, then we also are incentivized to check like how a MEV game is actually played on Algorand, and that's like the whole motivation of this research. So first I'm going to do a little bit introduction again of MEV and Algorand, but then I'll move on to our research plan and share some results that we have already obtained. So one way to think about MEV is that it's like if you are the next block proposer and you have, for example, this mempool, like what can you do to maximize your profits? So of course the naive approach is to let me just get the transactions which pay the most gas price, but is that the best that you can do? For example, in the third transaction, someone is doing an arbitrage and grabbing 1 ETH profits, or in the last one, someone is calling a vulnerable contract and just like draining it to get, for example, 10 ETH profits. And because I'm the block proposer, I'm the miner, like what stops me from just copying those transactions and issuing them myself and just like censoring the original transactions? Or for example, there is a price update made by an oracle on the fourth transaction, and we know that price updates can lead to liquidations. And because I'm in this privileged position of seeing this transaction and actually building the block around it, why don't I just issue a transaction right after it and be the first to do the liquidation and grab all the profits? And all these value that we can make, or a miner can make through these actions, through the strategies, is known as maximal extractable value, or miner extractable value. And in the last 2 or 3 years, this value, this incentive has turned out to be like the most prominent incentive affecting all layers of a blockchain, from like consensus security to economics. And because of this great impact, you see that Ethereum Foundation is also studying it along with a lot of other groups. And here at TUM, we are also studying MEV on Ethereum, on different blockchains, looking at different aspects of it. And of course, MEV, if you are a privileged actor like a miner, then you basically have that last look opportunity. You have more power, but there's nothing stopping someone just monitoring the mempool from actually issuing these same third and fifth transactions or just attempting the same strategies. The only problem here is that he now has to convince the miner to include his transactions before the original transactions. And on Ethereum, this is done through transaction fees or gas prices. So you give a higher gas price to incentivize the miner to include your transaction first. But not all blockchains have this fee-based prioritization. As we'll see, Algorand is, for example, right now a first-come, first-served kind of blockchain. So the order of the transactions actually are based on the order they were received. But and what this means is that then you have to rethink about all the MEV strategies that you develop. And one thing that you will see at the end of this presentation is that it takes longer than a day to learn about MEV. So this is a nice chart by Flashbots, the premier research group on MEV, showing the amount of value extracted before merge on Ethereum in the last 2 years, more than $670 million. And yeah, as I said, because it's such a powerful incentive, it then actually motivates people to vertically integrate with different participants on the supply chain and grab as much value as you can. And this is definitely then threatening the whole like core properties of a permissionless blockchain, like decentralization, for example. And of course, then the miners here, or the block proposers, they're not actually actively extracting the MEV themselves, but they're just letting people to compete on extracting MEV and now let them pay you, basically. And here we see that they just made, like, out of that $600 million, $240 million just by the payments they get from these MEV searchers. So you can see how the value flows. And yeah, one thing that we have to consider about MEV is that the value that we have quantified here, these are just some value we quantified because we defined some heuristics and we checked some certain protocols. But you know, the heuristics, they're not telling the whole picture. So there is actually an extracted value that we didn't quantify yet. And on top of that, like, a blockchain is basically a state, right? A state machine, and the total value resides there. We actually can never potentially know, like, the whole picture of the existing value there. So the extractable value is actually much larger than the extracted value, and you can think of maximal extractable value as the border of that extractable value. And of course, as I said, MEV doesn't stop at Ethereum. It is taking shape based on how the blockchain is defined. On Ethereum, it was initially played as a higher fee means higher priority kind of game, but then, as also mentioned recently, solutions like the Flashbots auction developed to take that MEV extraction game off-chain and has different properties for better extraction. But yeah, initially it was a fee-based game on Ethereum. But then, as I said, not all blockchains are prioritizing transactions based on the fees. There are chains like Algorand which order transactions based on the order they were received. So first come, first served, for example. And then this means latency wars. So then you have to have the smallest amount of latency to do all these strategies that you want to do. But still then, not all strategies are available. And we will see why. So as I said, yes, Algorand is a first come, first served blockchain with minimal fixed fees. So the fees are right now only to, like, prevent spams. And Algorand has some nice properties to itself. It has I would say, a novel consensus mechanism paired with pure proof of stake, where there are, like, no fixed set of consensus participants and no certain amount to be staked to join the consensus. And it uses these verifiable random functions to determine the block proposers in a secret way, I would say, and in an unpredictable way. Because on Ethereum, for example, you know 2 epochs beforehand, so like a couple of minutes beforehand, who is the block proposer in a certain slot in the next epoch. But on Algorand, it's basically like all calculated on the fly. So you cannot define a strategy or design a strategy beforehand. And yeah, one interesting property of Algorand is that right now the demand for block space is less than the available space, so there is no congestion. As we have seen on Ethereum, for example, they are designing these transaction fee mechanisms to consider congestion and, like, internalize the value. But on Algorand, this is not the case right now. And one other interesting property is that Algorand currently doesn't reward the consensus participants, so no block rewards for block producers, and also the transaction fees are not paid to the producers as well. They are collected in a pool managed by the Algorand Foundation. So then we can conclude that there's no actually direct economic incentive to propose a block. Like, why spend energy on it when you cannot basically get any block rewards or transaction fees? And this was, like, one of the first things we thought about MEV on Algorand. So maybe then block proposers are incentivized by the power they have with ordering the transactions in a block, because then they are in the privileged position to extract MEV. And here we say Algorand is currently a first-come, first-served blockchain because in congestion times, actually, you can prioritize your transaction with fees. So it's kind of like a hybrid mix of fee-based and order-based transaction prioritization. And yeah, all these properties then make it interesting to analyze MEV on Algorand, and that's like our, that's the point where we are focused on. Some properties of Algorand, one interesting one is the block time. It's pretty fast. Again, this then changes whole the MEV dynamics, and the transaction fees are pretty minimal. And studying MEV on Algorand, so this is a problem that I've been thinking about for some months now, and it's just never ending basically, because you initially start with, okay, let's first quantify, arbitrage, and then you ask yourself, well, maybe people are not actually extracting all the value out there. Like, what about value which was not realized? And then you say, okay, these are the values that users can extract, but what about block producers? Is there anything else that they could do? And then you think about, okay, how can we actually prevent this happening? And yeah, it just grows and grows. And that's why this study is a work in progress. I don't know if it will ever end. It will definitely end when I finish my PhD, but yeah, we'll see about that. And yeah, so I have around 8 minutes left, or less? Less? Nice. Okay, 4, and we didn't even yet start talking about the research. Okay, so the first thing is, we started with, let's attempt to quantify this value, and quantifying it then gives you a picture of how much MEV activity is going on. And the simplest way to approach quantification is, for example, for arbitrage, defining some heuristics. And the canonical way for this is to given a transaction with n swaps, you can say, okay, there must be multiple swaps because it must be an arbitrage. It won't be an arbitrage otherwise. And then the initial token that you input must match the output token. And of course, the amount of the output token at the last swap's output token must be greater than the first swap's input token, so that you make profits. And of course, this doesn't cover the whole picture. That's why the difference between the extracted value and the quantified extracted value. But at least this gives us an intuition about how much arbitrage exists. But as I said, quantifying the existing value doesn't cover the whole picture, because there is an extractable value which was maybe extracted, maybe not. And to analyze the extractable value, we take the state and we run cycle detection algorithms or convex optimization problems solvers on it to find, okay, actually this could have been done to extract that much value. And this would then we could compare this with the quantified value to see how much value was missed. And we did a work on understanding the first question we asked was, okay, if there is a DeFi market running on Algorand, then because there are multiple DEXs all with similar pools, there must be someone doing the arbitrage, leveling these prices. So we track the prices on Algorand of the same pools on different markets, and of course, we see that most of the prices are similar to each other, and we also compared it with a spot market price like Binance, and we see that people are actually doing the arbitrage. So okay, this hints us that there is actually MEV activity going on Algorand. And we developed a formula actually to see, given a spot price, what should be the DEX price so that there is a profitability with respect to the fee of that DEX. And you can see the derivation of that formula in that link. But basically here we can see that the gray lines, I hope you can see them, they represent minimum or maximum DEX price that should be with respect to a spot price, so that there is actually a profitable arbitrage opportunity. So for example, if and the blue line is the DEX price, so whenever it's above the min DEX price line, that means, okay, given a spot price, the DEX price is enough expensive so that someone should actually attempt the arbitrage and they can make value. And the red vertical lines here show that anytime that blue line is outside that gray range, there is an extractable value, and the red lines just quantify that. And you can see a further explanation of this in my student Jonas's poster presentation today. And if you sum this value up over all dexes, then you will actually get an intuition about how much centralized exchange, decentralized exchange arbitrage exists on Algorand. But as I said, this is extractable value. It's not actually the extracted value. And yeah, I'm gonna wrap up.
Thank you.
And of course, then you start evaluating, okay, because this is a first come, first served chain, then some strategies are limited. You know, I cannot see a transaction in the mempool and offer a higher fee to front run it. I have to actually optimize my latency with the nodes and like get the transaction as fast as possible. But you know, this requires an analysis then, and yeah, this is like a research objective we have to see, okay, what are the like latency impact on this whole MEV game. And the final thing we do is we look at privileged extractable value. So, you know, like what other things that you can do if you're a block proposer or you're a relay node controlling the traffic, because then you are not limited by first come, first served, because you determine the order of transactions and everything. And this then introduces whole different MEV dynamics. And yeah, this is again something that we're looking at. And yeah, final slide. I'm gonna analyze MEV on Algorand. Okay, it takes longer than a day.
Thank you.